Today we're going to build on what we learned yesterday about exponential equations. But before we do, I want to point out a couple of kind of odd looking cases that you might come across. So if you remember from yesterday, when you're solving an exponential equation, you want to make sure that you write both sides in the same base. And I know I also said that we always want to look at the smaller base and try to write every single term or write both sides in terms of that smaller base. But when you have a base 1, it's always just going to be 1. So there's no way to raise 1 to some power and get a 2. Because if I do 1 to the first power, well, that's 1. If I do 1 to the second power, that's also 1. If I do 1 to the 20th power, that's also 1. So this is not a base that we're ever going to use to rewrite in. So you're going to look here at my 2. We're actually going to use a base 2. So I'm not sure if you recall that property of exponents when we have an exponent raised to the 0 power, when we have a base raised to the 0 power, that's equal to 1. No matter what the base is, anything to the 0 power equals 1. So no matter what the base is over here, if you see a 1 on the other side, you're going to just use the base that you see and then raise it to the 0 power, and that automatically makes it 1. So if I was going to solve this problem here, I'm going to write my 2 to the negative 3x, and then I'm going to rewrite my 1 as 2 to the 0 power. So now my bases are the same. Bases are the same. You can basically just ignore them because if the bases are the same, the exponents have to be equal to each other in order for it to be a true statement. Okay, negative 3x equals 0. Just go ahead and solve that by dividing by 3. X is 0. Here's another example. Okay, so again, we're never going to write something in a base 1 because there's no way for us to get a 4 out of 1 to some power. So all you're going to do is you're going to keep this side, 4 to the negative 3n equals, instead of 1, we're going to write that as 4 to the 0 power because that equals 1. Okay, so now you're in the same situation as the last problem. Bases are the same, the exponents are equal. Okay, so another kind of special case you're going to run into is whenever you see a fraction here. So another property of exponents was our negative exponents. So I'm not sure if you recall, if we had something, whatever the base is, and we had it raised to a negative exponent, what that means is this thing needs to go to the other side of the fraction bar. So instead of x to the negative 1, we can write that as 1 over x to the first power. Okay, so anytime you have a negative exponent, you're going to take that base and you're going to put it in the denominator. So if we think backward from that, well, if I have 1 over 64, and I want to write that as an integer base, I don't want to use a fraction, then I'm just going to make this 64 to the negative 1. So you just kind of have to think backward. So anytime you see a problem where you have 1 over something, that should raise a little red flag for you that whenever you rewrite your base, the exponent is just going to be negative. So for this, we have to actually still decide on a base to use. So what you want to do is you want to just kind of focus on the 64 and focus on the 8 and think about a number that I can rewrite both of those numbers in. So I know that if I raise 8 to the second power, I'm going to get 64. So I'm going to go ahead and use base 8. So if I do 8 to the second power, this is 64. Well, that's not what my base is it? My base is 1 over 64. So instead of making it to the positive 2 power, we're going to make it to the negative 2 power. because 8 to the negative 2 is the same as 1 over 8 squared, and 8 squared is 64. So you can replace your 1 over 64 with 8 to the negative 2. Okay, so here's what that looks like. So we're going to go 8 to the negative 2, but we had this exponent here already, so don't forget you have to multiply. Equals 8. And if you don't see the exponent, remember it's just a 1. So now we have our bases the same. So you can cancel off your bases. Negative 2 times 2k, this is going to give me negative 4k equals 1. And then go ahead and divide both sides by negative 4. So k equals negative 1/4. And you can always plug that back into the original to check out your solutions to make sure they work. So let's do one more of those. Okay, so here's another one where I have 1 over a number. So this should be a red flag here. I know I'm going to use a negative exponent. As soon as you see 1 over a number, I know it's going to be a negative exponent. Okay, so we're going to decide on a base here. The smaller base here is 36. If you raise 36 to the second power, it's 1296. So that's way too big. So we need to go down a base. So we need to get a base that we can rewrite and get a 36 and a 216 out of. Okay, so let's try base 6. If I do 6 squared, this is going to give me 36. If I do 6 to the third power, this is going to give me 216. But my base isn't 216, it's 1 over 216. So all I got to do is make that exponent negative. Okay, so 6 to the negative 3 is going to go right here in place of this. So we're going to rewrite it. So 36 is going to be rewritten as 6 squared, but then you have to multiply by the exponent that was already there. And then 1 over 216 we're going to use as 6 to the negative 3. But you had a negative exponent, or had an exponent there already. So now my bases are the same. That means the exponents are equal. Ignore the bases. 2 times 3x is going to be 6x equals, and then this is going to be positive 9x. Okay, and then if you divide both sides by 3, x is just 0. Okay, so building on from yesterday, we're going to talk about what happens when we have more than one base on a side. So today is just simply multiplying. So if you recall your exponent properties, whenever you're multiplying the same base, you add your exponent. So if I had x to the third times x to the fifth, this is x to the eighth. So it's the same thing if your bases are numbers. If I have 2 to the third plus 2 to the fifth times 2 to the fifth, that equals 2 to the eighth. Okay, so your base doesn't change. You can just condense it down and just add your exponents up. And then you have a single base to a single exponent. Okay, so if you notice, we have 2 bases on this side, and they're both being multiplied, and then we have a single base on that side. So you still just need to do what you did yesterday and decide on a base to use. Well, 81 is too big. If you raise 81 to the second power, it's way bigger than 243. So you want to go down a base. So maybe you want to try base 9, because 9 squared is going to give you 81. So that would work for your 81. If you do 9 to the third power, that's going to give us 729. Well, 729, that's way too big. So we can't use base 9 either. So we want to go down one more base. So maybe we try base 3. So I can do 3 to the 4th power, and that'll give me 81. And then I can do 3 to the 5th power, and that'll give me 243. So that's what base I'm going to use. So replace your 243 with 3 to the 5th. But since we already had an exponent there, we want to multiply. And then you're going to replace your 81 with 3 to the 4th. But we already had an exponent there, so you have to multiply. Equals, erase this stuff out of our way. 81 again is 3 to the 4th. There was not an exponent there, so we don't have to multiply. All right, so we have still multiple bases on this side, so we're going to condense this down. So we want to make this 3, and then we're going to add these exponents up. Okay, so if you do 5 times negative 2k, this is just negative 10k, plus this exponent, which is 4k, equals 3 to the 4th. So now you have a single base on each side, and now you're ready to solve. All you do is drop down your exponents, and solve. Divide both sides by negative 6. So k will equal, if we reduce 4 over 6, that's negative 2/3. So it's the same thing as yesterday, but you just kind of have that added step where you have this extra factor here, and then you have to add your exponents. Let's try another one. So I'm looking at this one, a 36 and a 216, so I'm going to use base 6. So 36 is 6 to the 2nd power times 216 is 6 to the 3rd power, but we had an exponent already in the problem, so you want to multiply, equals, okay, so here's a 1. We just talked about this a couple minutes ago. Anything to the 0 power is 1. So since my bases here are 6, I'm going to go 6 to the 0, because 6 to the 0 equals 1. Now I have my bases the same. On this side, I need to add my exponents. So it's 6 to the 2 plus 6k equals 6 to the 0. Now your bases are the same. You can cancel them off, solve your equation. All right. And then the last one I have for you is this one right here. So this we're going to go with a base 10 because we have all these zeros and ones here. So look, this one has 1, 2, 3, 4 zeros. So I know this is 10 to the 4th power. So this is going to be an exponent that's negative because this is a fraction. So instead of 10 to the 4th, it's going to be 10 to the negative 4 times, we have 3 zeros here, 10 to the 3rd is 1,000. But then we already had an exponent, so you got to make sure you multiply. And then this is 10 to the 1, 2, 3, 4, 5, 6. 10 to the 6. But we already had an exponent there, so you have to multiply. Okay, so now you have everything to the same base. You're going to add your exponents. 10 to the negative 4 plus, and this right here when we multiply will give us 6x. 10 to the 6x. So our bases are the same. The exponents are equal. Okay, so you want to try and get your variable on one side, so let's subtract 6x from both sides. Negative 4, these cancel, equals, well, this just gives me 0. Okay, so this is not a true statement. This happens sometimes when you solve exponential equations. So if you solve the problem, you did everything right, but this doesn't make sense. This definitely is not true. So this one has no solution. Okay. All right, let me know if you have questions.